Okay, I'll just wait one more minute and then we'll get started.
Mm-hmm.
Okay. Well, welcome everybody to the Privacy Enhancement and Assessment Research Group meeting for IETF108, our first online meeting using the new Meet Echo tool. I'm Sarah Dickinson. Also chairing today are Shivan Sahib and Chris Wood. As per usual, this session is subject to the Notewell, so please read and digest that. Seeing as we are using Meet Echo for the first time, please do bear with us if you run into any technical hiccups along the way, as this is our inaugural flight with the new tool. Just to remind everybody who's participating that this session is being recorded, both the audio and the video, so please be aware of that. The audio, the blue sheets are automatically populated by the data tracker, so we don't have any separate work to do there. In terms of queuing during the presentation, what we would like to ask is that if you want to make a comment on any of the presentations, please enter the queue by using the raise hand microphone and optionally the raise hand video. We have a lot of short presentations today, so our intention is to hold off taking questions until the end of each of the presentations. And even though it's a remote meeting and we have some identification, please still continue to identify yourself as you start speaking, just to help all the other participants. We have noticed requests that people do use headsets if they do want to share their audio, because we believe that works much better with Meet Echo than a hands-free setup. And otherwise, if you're not intending to share any media, please have your audio muted and your video off by default. As with other meetings, there is the Meet Echo chat and the Jabber room, and we will still be taking questions there in case you have problems with your audio or you just prefer to do it that way. And if you do, please prepend your comment with Mike if you actually want it brought into the queue. And Shivan is going to be our Jabber scribe today. He's going to watch the queue and bring any questions there that arise via the chat. Okay, so our agenda today, I hope I've covered most of the administrative stuff so far. We do have a note taker. Chris, thank you very much for that. Our agenda today is quite packed. We have 4 presentations of 15 minutes each on various new work topics. And then after that, we have 3 presentations on updates to drafts that are under review. If anybody has a comment on the agenda, could I ask you to jump into the queue now and make your comment? Just, or do it in the chat room. Okay, I'm not seeing any comments on the agenda, in which case I will switch over to the first presentation today. And that is being given by Stephen Farrell, and it's on the topic of testing apps for COVID-19 tracing. So Stephen, these are your slides. If you just want to say next slide when you need me to progress them.
Sure.
And let me, right, let's get your, turn my video off.
I hope I hit the right thing for requesting video.
And do you want to share your video, Stephen?
I think I'm trying to.
You're trying to share your screen, which is exact same mistake I've made many times.
Oh, okay. Pardon me.
You want the little camera, not
So
the...
leave that, do that.
Yeah, let's go.
There we go. Okay.
Perfect. Thank you. Go ahead, Stephen.
Great, thanks. I'll flick through these slides quickly. Happy to take questions later. So this is work done by myself and a colleague, Doug Leith. And to be honest, Doug did most of the smarter stuff here, not me. Next slide. So the background here is we clearly have a pandemic. In Ireland, we'll talk a bit about it. So the Irish government, the Health Services Executive, essentially, are the public health authority. Generally, they're perceived locally to have done a good job. And that kind of impacts on what happens when you try to deploy these kind of applications for COVID tracing, which kind of started with a March 2020 paper referenced here that basically asserted that a mobile phone app could make this all better. It would be nice if that was true. We're not sure it's true, nor what the security consequences are. So basically, we wanted to set up a little project to examine that. And our project is basically taking the approach of not espousing any particular method for tracing, but rather just to be testing what's been done. So although we're talking today about the Google Apple API, we started out by looking at some of the Singapore work that predated that. I guess worth noting maybe is that the March 2020 paper, Ferranti et al., way back ago in DTN times, about 2011, there was a flu phone proposal from came out of John Crowcroft's group. So it's, that the idea of using phones and Bluetooth for this kind of thing is not that new, although this is obviously the first time it's been tried. Next slide. So the next slide is about some caveats. So yeah, this is a fast-moving area, and Google and Apple have released some additional snippets, is the way part of it is described at least, of code. I haven't really looked at them yet, but a lot of what's going on here is changing rapidly in a matter of weeks. So again, take the results and the slides and so on here as a snapshot. And again, we have to be understanding about lots of decisions here were made quickly in the face of a lot of uncertainty, people trying to react to the pandemic. So there's a lot of change. There will be more change. So we should be we shouldn't be blaming people, but trying to find ways to fix things or improve them. So next slide. This is just an overview, and so we can go straight on to the next slide. So we have a few slides about the Google Apple exposure notification system, which basically is what seems to be getting traction and reasonably wide deployment. It's the apps running for this are essentially in two parts. One part is the app code, which is developed by a public health authority. So for example, the Irish Health Services Executive. And the second half is the exposure notification API implementation, which is from Google or Apple on the relevant platforms. And basically, the app handles the interaction between the handset and the public health authority servers in a particular region. And the API implementation within the operating system somewhere handles managing Bluetooth beacons, so you don't drain the battery, doing the kind of crypto at low level stuff. That's essentially the split between them. And part of the reason for that is that doing the Bluetooth stuff well as devices go to sleep and all that has been clearly found to be problematic unless you're inside the operating system. So how does it work? The handsets basically generate a new symmetric temporary exposure key every day. They, every 250 milliseconds, they send out a Bluetooth beacon, which has a rolling proximity identifier value. That's essentially a value derived from the daily key that changes every 10 minutes, and the crypto derivation's there. The crypto for that part looks fine. The beacons also include this rolling value that changes every 10 minutes as the Bluetooth MAC address changes. It also includes an encrypted transmit power, which is helpful for figuring out, trying to figure out proximity. And although that's just using counter mode, so it's unauthenticated encryption, that seems okay. If it was the case that any random app on the device could spot the outbound beacon value and manipulate and send another beacon with different transmit powers, that might be a problem, but apparently that's not possible, at least on Android. The handsets listen, although they're sent every 4 times a second, the handsets only listen about 4 seconds out of every 4 minutes for beacons. And I presume that's battery saving. And then they record the beacon value, which includes the RPI and encrypted transmit power and the received signal strength indicator that the inbound beacon had. And the idea basically is everybody's running these apps. If a person tests positive, then their local health authority, the medics who tell them that they're tested positive, will give them some kind of authorization code, which allows them to upload the the temporary exposure keys they've used for the last 2 weeks or so to the Public Health Authority, who then publish those. Every other handset, so Bob in this case downloads them every few hours or so, and they can compare against the stored beacons and determine if there was a proximity event. So next slide. Now the stated goal of these apps is essentially, at least in Ireland, very similar to what the advice that the medics give about when you might have been in contact that seems to be used by the manual contact tracers. So the stated goal of these apps is to detect where the two handsets within 2 meters for more than 15 minutes, based essentially on looking at the signal strength and matching the RPIs and texts and so on. I don't believe that can be reliably done, as we'll see. But the details of how they do it, we'll skip through quickly. But nonetheless, there's essentially a mix of the transmit power and RSSI to derive an attenuation figure. The API implementation doesn't directly say that was a proximity event or not. What it does is it gives back attenuation duration values, which are described as in that complicated bullet there. The thing to note here is that the health service or the health authority app sets some thresholds, gives those to the API. The API does the matching of the text and RPIs, and then returns, if there is a match, attenuation duration values, which essentially is how in 3 buckets of nearer, in between, or further away, how does that match to the thresholds given? And then it's up to the app code, not the API implementation, to decide if the user should be notified and advise the user to isolate and get tested and so on. So next slide. There's some governance issues with this that are worth noting. Essentially, Google and Apple are in total control here. There are some reasonable justifications for that, because we don't want 200 different schemes. We absolutely, because of the realities of the mobile ecosystem, you absolutely need the people who control that, or mostly control that, to be involved, and so on. However, given that Google and Apple are in control, one of the things that Google in particular have to do is improve calibration across the tens of thousands of handset types. And what that means is that because we have the thresholds set by the health authorities and the matching done by the API implementation, as Google ship new updates to their API implementation, that it affects the results as to whether you get notified or not in a way that's outside the control of the health authorities, which kind of seems like a weird design. So revisiting that governance, and I have no idea how you improve it actually, but revisiting it in some way seems like it might be wise. Next slide. Lastly, about the background before we come to some sort of results. The actual system itself, you have to think about how would you measure this. Mostly in the media, you see about numbers of downloads, or that there's this fake thing that you need 60%, which is not true. The actual questions that would be interesting to ask are, how many people who wouldn't otherwise have been found by manual contact tracing get notified? How much quicker are those that would be found notified because of the apps? How many people turn out to test positive versus a similar sample of the population at that time? And it's through those kind of metrics that we might be able to figure out, do these apps work? And as far as we're aware, there's no health authority who has deployed is currently actually measuring the kind of things that will allow you to tell if this stuff works or not. My own suspicion at this point in time is, unless that changes, in the end, we'll never know if these things actually prove effective or not, but we'll see. So next slide. One of the things we discovered early on, looking at the Google system and also the Singapore system and the NHS proposed system that didn't get deployed, was a lot of these things are dealing with beacons. You have replay attacks. They're fairly obvious. What we did was to look at in an Irish model. So basically, in kind of early May, I think it was, we looked at the number of people who are getting put through a COVID testing station. We looked at statistics for how many of those were positive. We looked at statistics for how many people tended to be in a hospital emergency department for how long, and basically concluded that if you mounted this replay attack in that context, then essentially by picking up the beacons at a place, the COVID testing station, where you expect to see some positive ones, you had an amplification factor of 4 by spreading those beacons in an emergency department. And a 4 is very conservative. It could easily be much higher, and those could be healthcare workers. So the attack is obvious, hasn't been mitigated at all, as far as I know, and hasn't yet happened, luckily. I can't imagine that will continue for too long. Next slide. So measuring deployments is a thing we're also starting to do. It's basically because of this set of exposure keys are public. We can download them, count those. And so we're currently doing that for a bunch of countries. You can kind of see the count there. It's still too early to draw conclusions from this. And this won't allow us to say these things do work. It might allow us to say that in some cases they seem not to work. And even so far after a few weeks, it does seem that there's some mismatches between the number of cases being declared positive for certain countries versus the percentage of the population who have installed these apps versus the number of texts that are being uploaded. So there does seem to be some discrepancies, but it's too early to say. Maybe after a month or so, another month or so, we might be able to come up with some interesting results based on this. So next slide. So like I said, the measurements themselves can't tell us if it works. One question to ask is, does this proximity stuff work, in fact? So we did a bunch of tests with, we had like 6 different handset types. So we did pairwise tests, giving a matrix of 36. We only could fill in 33 of the cells because we didn't have 2 handsets for every type. And we tested them at 1 meter apart for more than 30 minutes, which should never produce a false negative, you would imagine, but it can do. So we did the initial test in early June, and on the bottom there, you can see that you can get a bunch of false negatives. I'll explain that a little bit more in a second. In the middle of June, Google started to look at the calibration issue, which is what the cause of these false negatives is, that essentially the different device types, when you look at them pairwise, they're not calibrated the same and you get weird answers. So what we did was, in our early June and late June tests, we applied the thresholds. So you remember I mentioned that there's the apps give the API 2 thresholds and get back 3 buckets. So we applied that to these tests. And you can see that in early June, like the number of false negatives is outrageous. In late June, if you look at the middle column there with the 0 added noise, it's getting better for sure. And if you had, if you subtracted and had stronger or less attenuation by 10 decibels, it would look very good. However, if you add 10 decibels to this pretty ideal case of 1 meter apart with no obstruction, of noise, where I'll talk about noise in a second, then we still get a lot of false negatives, even at 1 meter apart. So next slide. So how might we get some noise? One way, which is covered in this particular document, this tech report we released, is just due to orientation. And because I guess handsets package antennae in different ways, the transmit powers are different. We can get noise basically just purely due to orientation. And I don't know how to model that correctly across all the possible handset types. And there's other types of noise you'd also have to model. But even with this thing, it's hard to see. You can see the diagram on the left there. We have, I can use my mouse, but I guess you can't see it. But there's a kind of a circular diagram showing the different angles. And then to the left of that, yeah, thank you. And to the left of that shows you the average kind of attenuation values you get at the different angles. So you can see there's about 20 decibels of difference. On the right, you get to enjoy a cat video if you like. What we did was, that's the environment where I did all these pairwise 1 meter tests. And just to see how orientation affected it, what I did was I took the near handset and put it on a turntable, so a record player. And let it rotate at 33 RPM. And the graph there shows you the raw RSSI values. So the left-hand side of the graph, which is mostly red, shows you the stationary 5 minutes. And then when you have the thing rotating, you get on the green side there is the when it rotates. And what you can see is you get about 10 decibels less noise in some cases, but it spreads out. So there seems to be noise added just due to the rotation. And that's when we add that noise into the basic things, we still get false negatives at 1 meter. So you've got to wonder. Next slide. So that's kind of artificial. So we also did a bunch of tests: walking, cycling, sitting on a park bench was interesting. If you have phones in your back pocket and you sit in a metal park bench, the signal goes to 0, essentially. But 2 of them are really more noteworthy because these are scenarios where you would imagine these apps, if they worked, would actually help with real contact tracing. And that's like on a bus or on a tram. Now, unfortunately, when you add the kind of metallic tube surroundings, then that affects the BLE distance estimation kind of badly. We documented that for the bus. The picked 2 diagrams here for the tram, shows you on the left-hand side the kind of layout of seating. So we had people sitting with phones in hand, trying to do something with the phone, as people normally would in public transport. And then we had a bunch of people do that for a quarter of an hour. Then we shifted positions with the same people holding the same handsets, did that a few times. And overall, we managed to derive a bunch of kind of values for what would you or would you not be notified in those scenarios. And the false positives and the false negatives essentially are pretty much the same and increase the same, which is with the different thresholds you might use, which is what the right-hand side shows. So it's essentially kind of random in that environment, and that seems like a pity for these things. Next slide. The other question we looked at then is what traffic is being sent. Only on Android. We have we don't have setups for exploring Apple at this point or the time. So we looked at the Android implementation of the API provided with Google as part of Google Play services. So if you disable Google Play services, then the apps just won't work. So we man in the middle of them, which is a horrible thing to do, but we did it. And then did unpinning and capture the traffic traces from the apps and from Google Play services. And overall, the apps behave pretty well, but Google Play services less so. And the report is linked there. Next slide. So we did about 7 or 8 apps. To take the Irish one as an example, because it's closer to home. And in all the tests we did, we just did the onboarding and downloading text steps. We didn't ever try and pretend to be infected and upload keys, because that could affect something. In the Irish app, I mean, it seems pretty clean, except there's a use of an authorization HTTP header when you're downloading these texts, which is pretty much unnecessary, and nobody else does it. But it's kind of standard mobile app development practices. So I think that's why they've done it. But they have a data protection impact assessment that says they don't store any of that kind of information. So it's not great for the protocol, but it probably in practice is not real damage. One thing they do is in the Irish case, they allow uploading of metrics, which is kind of has a mix of DevOps data and medical information, including whether or how many times the user's been notified by the app that they may have been in proximity. We kind of recommend keeping those in separate security contexts because they're kind of different. And then there was some path not taking code with calls to Google Firebase. So basically, if you look at all these apps, like 7 or 8 of them across Europe, Germany and Switzerland are pretty good, and Ireland would be kind of mid-table, and some of the others had some less desirable features or weren't open sourced or whatever. But none of them are really, really terrible. However, next slide. We were interested in what Google Play services were doing, so we turned off everything possible. Usage and diagnostics. If you click along enough, there is a way of turning down usage and diagnostics in Google Play services. We turned off every other Google thing, went to the Google dashboard to make sure there was nothing showing there. And basically, we tried to find out what's the very minimal configuration of a handset that can still run these Google Apple exposure notification apps. And even in that configuration, about every 6 hours, Google Play Services calls home with essentially all of the long-lived, unchangeable identifiers you could kind of imagine, all bound together, so that even if you give your handset to your child and change the, no matter what you change, you do factory resets, some of these identifiers will live on and provide a chain of connectivity. And then in addition, every 20 minutes, there's another call to an API that is linked to the check-in call that then allows, in theory at least, would allow IP-based geolocation. And essentially, it means that those persistent identifiers are being tracked at the 20-minute kind of frequency across all the different networks you might join. There's lots of additional telemetry in those messages that's binary, we don't understand. And what's notable here is there is no published data protection impact assessment for the Google Play Services implementation of the exposure notification API. Nor for Google Play Services. All of the apps have done that because their populations are such that they're government still. So that seems like a pretty bad mismatch to us. And Google Play Services, of course, is closed source. Yeah, so basically, I think that creates an issue for people who care about this kind of stuff. Next slide. Just
a time check, Stephen. We're a little bit over.
Sorry, this is my last slide. These apps have been deployed. The replay exists. I don't think the stated goal of the Bluetooth proximity is really the correct one. If you care about Google tracking you and you want to run it with these apps, you have a new problem, I think. We don't have information with Apple, and things can be improved with additional documentation, maybe some kind of quiet mode, and perhaps revisiting some of the governance kind of issues. The next slides are just some resources. The only notable thing is we have some code that we haven't quite released because it would allow making this replay attack much easier, but we're happy to share it with anybody who's a researcher. And that's it. Thank you.
Great. Great. Thank you very much, Stephen, indeed. I think we just have time for one question. So I'm going to ask Bruno to accept your audio and your video. If you want to go ahead. Bruno, you should have the cue now. I'm not hearing you, Bruno.
Sorry, I didn't actually have a question. I just clicked on the button accidentally.
That is no problem at all. Let me.
Well, that was an easy question.
Yeah, that was a piece of cake. Okay, so we do have another person in the queue. That's Jeffrey. So I'm enabling your audio and your video. Please go ahead, Jeffrey.
Did you manage to file a bug with the site services folks? Or do you want me to forward this to them?
So we shared, before we published this, the last stuff, we shared that with some contacts in Google and in some of the health authorities. We didn't formally file the bug. I'm not. Yeah, I don't know if is it a bug that they're spying on us all the time deliberately and have been for years. I mean, that's the kind of question you'd have to wonder. Now, I mean, that's a pejorative description of it, but I'm not sure that Google would consider it is actually a bug, because I think they consider that they just added the exposure notification to Play Services, and Play Services already does that for what they consider reasonable ecosystem reasons. So I suspect they wouldn't agree it's a bug, but I think it's not a good feature. But okay.
Okay, thanks.
Sure.
Okay, I'm afraid we're over time. So Joey, if I can actually ask you to take your question to the Jabber room or to the list, or directly to Stephen if I can.
Yeah, I'm happy to answer questions, Jabber. So how do I unstop, or do you just boot me?
I can do that for you. Thank you very much, Stephen.
Okay. Cheers, thanks.
Thanks, Stephen.
Okay, so let's move on to the next presentation, which is by Stephen Valdez on trust token architecture. So I'm going to enable both your audio and your video, Stephen. Let's see how that goes. Okay, I can see you.
And hopefully you can hear me.
Yes, indeed. That's brilliant. Please go ahead and just let me know next slide when you need me to advance them.
Yep. So I'm going to be talking about Trust Token, which is a new API we're working on based on Privacy Pass and a crypto construction called PNB tokens, which is a token construction that allows some amount of private metadata. Next slide. Next slide. That's just an outline. So the problem we're trying to solve is protecting against things like denial of service attacks, bots, and spams in a way that is not painful for legitimate users, where they have to solve some challenge or do something every single time they want to perform an action. But also, we don't want to be relying on a lot of these cross-site tracking and fingerprinting vectors that are currently used in the industry. Next slide. So the existing way of doing this is, for the most part, you visit a website, the website decides that you need to prove some sort of trust or some sort of proof that you're a legitimate user. For smaller websites, they use some sort of trust provider, either a CAPTCHA or other form of bot guard protection. That provider sends you a request to do some amount of work, some proof of work, some challenge. You solve it, you return it, and then you get a verification saying that, yes, have successfully proved to some extent that you're a real person, either via solving that challenge or via any state the CAPTCHA might have on you from before. And this works great for the first time, and if you have to keep on doing these challenges every time you visit the site, then this adds a lot of strain to the user. Next slide. So a lot of these trust providers actually, after you complete a challenge, store some amount of third-party state, either in your cookies or local storage, that it can use next time to see that, oh, you've already passed a challenge, you've already proven your identity, and can use that to either give you a simpler challenge or just give you a token right away that says that you are good to go. You don't have to do the complicated figure out if this image is a hot dog or a cat or a cow. The problem here is that third-party state can be a massive cross-site fingerprinting and tracking vector, and if possible, we don't really need all the information that third-party state here provides. You really just need a single bit of information that carries whether or not you are trusted. Next slide. but you also want this like single bit of information to be something that like the trust provider knows it generated and that wasn't forged or copied or duplicated. Just doing a raw signature would give that part of the requirements, but does mean that the issuer can now, or the trust provider can track you between when you were first there and when you're now there again. So this is signature basically acts directly as a fingerprinting vector. Next slide. So the properties we actually want for this third-party state replacement is that it's unforgeable, that the client can't make more tokens, that it's non-malleable. This matters less when there's no metadata, but further on we'll get into why some amount of metadata might be useful. That it's unlinkable, since otherwise this is just a new form of tracking. That it's efficient because CAPTCHA providers and other trust providers end up generating and redeeming these tokens at scale, especially since they're used in all sorts of places like forums, places where ads are presented, places where there's user information being displayed, where you want to limit basically everywhere that you need these sorts of like DOS protections, which you don't want this to be a slow process, either for the client to generate and verify these tokens or for the server to be verifying and generating these tokens. But you also want this to be a verifiable token in that the client can make sure that there's not extra information being conveyed by this token that it doesn't know about. Next slide. So most of these properties we get through a primitive called privacy pass, which is part of another working group in the IETF, which provides basically everything except non-malleability of metadata, which we'll get into why this is useful later, and privacy pass by itself pretty much solves most of this problem. The problem turns out to happen, next slide, that we don't only want to be providing, yes, this user is trustworthy, because if we just provide that, then this is a very easy signal for attackers to, I go attempt my new attack against this detection algorithm, this CAPTCHA, see if I get a signal, yes, and if so, like that is a very like immediate response. Like if I got a token, that means I've bypassed this identity provider. And the current world, like third-party state and the challenge verification is actually more of a continuous signal between like I am trusted or I am untrustworthy. So currently most trust providers don't immediately provide this feedback about, yes, you are trustworthy, you've like passed all my checks. And we want to maintain this like somewhat trustworthy or not trustworthy signal and just not have it a like single state. Otherwise, like a month down the line, people will have bypassed all the new trust systems that use just the single bit of information. So the new property we really want is this one bit of information that can be used to say yes or no in a way that the client can't tell what the value of that one bit of information is. This is the concept we're calling private metadata. We need to provably show that like it's only a single bit of information that we're storing this metadata, which is why we need a more complicated scheme than just the privacy pass with VOPRF construction that privacy pass currently has. Next slide. So one way of implementing this is privacy pass uses a DULIC proof, a zero knowledge proof, proving that the issuer signed this thing with this key, and the signature is formed in such a way that the client can then blind it so that in the future the issuer knows it was signed but can't just copy the like signature, can't just use a lookup table from the signature that it generated to the signature of the final token. So the way we'd first thought about introducing private metadata is that the issuer signs with one of two keys, either a true key or a false key, and proves that it's signed with one of those two keys and no other keys. The client then verifies that proof, and still we have the property where the client makes a new token that has a valid signature that can't be compared to the previous issued token, but the client doesn't know exactly which key was used. The problem with this is that there are some attacks where if you have one token that you're pretty sure is a good token and one token you're not sure of, or one action you're not sure of whether it will give a good or bad token, you can get the issuer to sign things in such a way you can compare the validity of two different tokens and see if they are signed with the same key or different key. Which means that, like, if you have a actual real user and you've stolen one of their tokens, you can now verify that any future tokens are signed in the same way or in a different way. So the second thing we attempted, next slide, is to use this new PMB tokens construction, which is a slightly more complicated construction that uses both the privacy pass structure, which is you have one key that you sign a token and prove that you sign with that key, but you also attach another signature that is signed with one of two tokens and have a or proof proving that you sign with those two tokens. So it's basically the previous attempt with this extra key signature from Privacy Pass. And the thing that this protects against it is now we can verify like whether this token is valid at all, but as long as the issuer doesn't say what, as long as the issuer verifies that first and then figures out whether the token is a true token or a false token, it's able to hide the fact, prevent the attacks that require altering the token slightly to compare token values. The actual process is we check one of the signatures and then only then check the other signature. If you leak the fact that the second signature is invalid, then the issuer leaks some information about token comparison. Next slide. So this brings us to how trust tokens combines the like privacy press primitives and this PMB tokens primitive. Next token, or next slide. So the protocol we're using is this like 3-step zero knowledge proof from PMB tokens, using a optimization called batching, which lets you combine a lot of different DLUC proofs together so that a issuer can issue a bunch of tokens in one batch instead of having to generate a new zero knowledge proof for each and every token, since clients will usually want to ask for like 5 to 10 tokens, since that's the number of times they'll try to redeem these tokens before it comes and talks to the issuer again and asks for more tokens to be issued. Next slide. Another thing we have in the architecture for trust tokens is that there are sites that have lots of embedded resources, lots of things that want some idea whether you're trustworthy or not. But they're all in the same like top level context. Like one site might have at the bottom, you have your comment board, you have your advertisements, you have your like buttons and social media buttons and other heavy resources. And you could just have the client send one token to each of these resources and then they themselves go redeem it and do this whole process. But one optimization is that the client itself redeems a token and like asks it to be redeemed for like this website and this time. And that might be a sufficient proof that the client had a token that the downstream consumers might be willing to accept that instead of having to do the entire crypto protocol where it goes and talks to this third party and have to deal with the QPS of having to redeem a token for every action. And this provides a nice optimization, though at the loss of, on one first party, you have to trust that multiple other entities on this page are using the same redemption record. There's also a slight privacy issue here in that like every third party on this site is getting the same redemption record, so you can correlate across those, but you already have these sorts of problems since the first party can already embed any data it wants into the third party requests on this page, as long as we're not allowing this set of third party requests to be correlated to the issuance spec when you originally got these tokens. Next page. Another problem is that trust tokens relies on the set of keys that are being used here to be anonymity sets. Like if a issuer was allowed to sign with 50 different keys, that means like for 50 different users, it could sign with a different key. And this would mean you have 50 different sets of anonymity. So like when I'm issuing, I choose one of those sets and like assign each user to a bucket, and that gives more metadata between your issuance and redemption. So we need some way of maintaining consistency of the keys that a issuer is using. One way, and what we're currently doing, is having a proxy that centrally fetches the key commitments and presents that to all the clients, so that we at least know that all clients have the same set of keys. Though this does have some amount of trust in the central proxy, and we have to make sure the proxy doesn't have any information about the clients, otherwise the proxy itself could be doing this division of the anonymity sets. Some extensions and alternatives we've been thinking of and are also part of Privacy Pass is some concept of a append-only log similar to CT, so people can audit the key commitments that a issuer is providing and making sure that these keys aren't changing too frequently. Next slide. So trust tokens as a whole is very close to Privacy Pass. These are the three main changes. We're hoping to bring some of these in line either from trust tokens to be more in line with Privacy Pass or in the other direction. We're working with the authors of the PNB tokens primitive to try bring it to the IETF, possibly in the CFRG, and having Privacy Pass be able to support multiple crypto primitives. We have a bit of a concept of redemption record, which is a delegated redemption in Privacy Pass, which we're wondering whether to make that a more general use case there. And key management is an open question currently in Privacy Pass. Next slide. So the next steps mostly are Privacy Pass is the main actual standard that all of this is based on. Our first working group session is on Friday, and hopefully we'll get some good docs and standards out of that. We're going to be experimenting a little while to see the ergonomics of trust tokens and whether it's actually useful replacement. And there's, on the web API side, some standardization efforts to try to come up with a standard for how you would interact with these protocols on the web. Next slide. And those are some links. Any questions?
Excellent. Thank you very much, Stephen. Do we have any questions for Stephen? And if I heard you correctly there's a working group meeting on this coming Friday for Privacy Pass, is that correct?
Yep.
Yep, okay. So folks who are interested in that can also join that meeting. We have...
Hey, Chris's question. Hey, Stephen, so Chris is asking if Google's KT system, is it a candidate for the registry?
I think it would make a good sort of registry for this sort of system. I think we'd probably want something, see about whether some sort of standardized version of that would work, whether there's either having it be part of the Privacy Pass working group or whether this is a more general problem that the IETF might want to pursue separately. But yeah, I think key transparency and cert transparency systems are something close to what we would like for a key registry optimally.
Okay, great. Thank you very much, Stephen. Thanks for your presentation. Okay, so we're going to move on to our next presentation, which is by Nate Matthews on de-anonymizing internet traffic with website fingerprinting. Nate, you need to also ask to share your audio as well as your video because they're separate media streams. So I'm going to accept your audio and your video as well. So we can see you and we can hear you. Please go ahead.
Great. All right. Well, hello, everyone. My name is Nate Matthews, and I'm a current PhD student working under Dr. Matthew Wright in the Global Cybersecurity Institute at the Rochester Institute of Technology. Our lab group primarily works on adversarial machine learning and its implications on anonymity systems. In particular, we've been working in the website fingerprinting domain for several years now. In this presentation, I'll provide a background introduction for website fingerprinting, and then later I'll discuss some of the attack and defense projects that our lab's been working on. So let's get right in. So next slide. So most of you are probably already familiar with the internet anonymity and Tor. Tor is a particularly popular and effective anonymity system that we oftentimes look at as a target for website fingerprinting attack. To provide anonymous communication, Tor incrementally creates a circuit containing a chain of 3 nodes that includes guard, middle, and exit relay. This circuit is encrypted and extended 1 hop at a time, such that consequently no individual node has the complete path information. So in this way, the attacker will fail to learn the user's internet behavior and the user's privacy is still preserved. Next slide. When a client is browsing the internet through some privacy-enhancing technology like Tor, the only visible information to an eavesdropper is the packet metadata produced by the network traffic. Unfortunately, this information is all that's needed to perform a website fingerprinting classification attack. Since this information is relatively unique for each website, an attacker can use this information to train a classifier to predict what website a user has visited, and ultimately learn of the user's browsing behavior. In order to perform this attack, the attacker simply needs to remain in a position to eavesdrop somewhere on the link between the client and the entrance to the Tor network, and have access to some modest computing power. Such an eavesdropper could be represented by your internet service provider, for example, or a compromised router on the network path. So the number of people that can perform this attack is quite large. Next slide. Website fingerprinting experiments are typically performed in two scenarios: closed world and open world settings. These scenarios describe what restrictions we have put on the experiment. In closed world experiments, the classification model is only given traffic from a small set of monitored websites. This experiment type does not accurately represent the real world performance, but is often used to benchmark models and techniques against one another. The open world setting instead makes the experiment more realistic by including samples from a large set of sites that were unseen by the model during the training. This unmonitored set of sites represents background traffic from the many millions of sites that the adversary is unconcerned with. The open world scenario is a more difficult task than the closed world scenario, and it's a better indicator for real world performance. Okay, next slide. Over the years, there have been many website fingerprinting attack proposals. Early attacks such as Kamul by Panchenko and K-fingerprinting by Hayes processed website traces into handcrafted features. These attacks use standard machine learning classifiers such as support vector machines, random forest, or k-nearest neighbor algorithm to learn to predict websites using these features. The attack process in these cases would first collect a small data set of representative samples for the website that you want to monitor, then develop a set of robust features to process the traffic into, before finally training your machine learning algorithm and predicting on unknown samples. In general, these works show that the features used to train the classifier are more important than the particular classification algorithm used. Next slide. More recently, researchers have begun to focus on developing attacks that utilize neural networks due to the high classification performance that these techniques demonstrate in the image domain. In particular, the state-of-the-art fingerprinting attacks against Tor use deep convolutional neural networks to act as a classifier for the attack. These models learn abstract features automatically from the raw traffic metadata and have been shown to achieve superior performance. However, these techniques generally introduced high data requirements, as more trace examples are required to train the model to extract meaningful features. The highest performing website fingerprinting attacks to date are deep fingerprinting and var CNN. Both attacks require at least several hundred samples for each monitored website to achieve optimal performance. Next slide. So here's a quick graph comparing the performance of fingerprinting attacks in closed world. The first three items are recent deep learning style attacks. And then the following three are prior machine learning attacks defined in earlier literature. So as you can see, each of these attacks are able to perform quite well in the closed world context, achieving up to near 99% accuracy on a monitored set of about 100 websites. And as such, represents a credible threat to client privacy. Next slide. More recently, website fingerprinting attack projects have focused on addressing elements of website fingerprinting that may make real-world application difficult. One chief goal is to continue to push the state-of-the-art performance, particularly in the open world setting. In the real world, the rate that a monitored website is visited is likely very low in comparison to the probability that any other background site is looked at. So consequently, a model with even a small classification error will produce an enormous number of false positives when applied in the real world. We call this the base rate fallacy. So to address this issue, the attacker's model must be tuned to achieve a very high precision to minimize the false positive rate, but must avoid lowering the recall so the model is still effective. One additional issue affecting the current state of the art are restrictions on the type of web pages used to represent a website. Current research treats the homepage of a website to represent the website as a whole. However, a robust attacker should be able to ideally identify a site using any web page belonging to that site. Prior experiments have indicated that the model efficacy is significantly reduced when many pages are used to represent a site instead of just a single index page. Now, the last goal for new fingerprinting projects has been to try to lower the number of samples required to train a classifier. So, for example, the time required to capture, say, 1,000 samples for each site, and say 100 site data set, could span up to several months when only a few machines are used. And this would be a huge barrier to actually performing a real-world website fingerprinting attack, because you need fresh samples. So to solve one of these problems, our group recently proposed a technique to drastically lower the data requirements. So next slide. So proposed in 2019 at the ACM conference on computing and communication security, our triplet fingerprinting attack is an attack designed for low data requirements. This is achieved through a usage of a special network known as the triplet networks. This attack is best described as a multi-stage attack that leverages both fresh and old data samples to train a robust model. So without diving too deeply into the network details, I'll go over each stage of the system. In the first stage of the attack, the adversary trained the triplet network to reduce traffic samples to abstract features using triplets. To perform this training, a large data set of old data is required. The old samples can be used because the goal is to train a neural network to simply understand what type of features can be used to represent a traffic sample. So the traffic samples don't need to be relevant to the actual monitored set that's being used in the later stages. The next slide. So then in the next training step, we use our trained up triplet feature extractor to convert a small data set of fresh samples to features, and then train a machine learning classifier, which is just a basic KNN distance classifier. So then we use this small data set to train this classifier because we're going to use this for the actual predictions in the next step. Next slide. So in the final testing step, we can use both our trained triplet feature extractor and our trained KNN classifier to predict on unknown samples. This technique allows us to reduce the number of fresh samples required from several hundred to just 20 instances per monitored site, while still achieving a competitive performance when compared to other attacks that we had reviewed previously. Next slide. So moving forward, it's less important for us to develop traffic defenses against these fingerprinting attacks. This goal can be especially difficult when considering that the state-of-the-art attacks do not use features that could be easily understood by a human. Nonetheless, there are several techniques that could be used to reduce classifier accuracy, which we'll discuss in the next slide. Next slide. Fingerprinting defense developers have two fundamental mechanisms at their disposal that could be used to modify traffic and confuse a classifier. The most common mechanism is that of adding fake dummy packets that are indiscernible from real packets. This obfuscates the traffic patterns but also adds additional bandwidth overhead that can congest the Tor network. The second mechanism is to add delays to real packets. These delays may adjust packet ordering and confuse patterns and timing. In particular, but these two different mechanisms, their effects on overhead can impact the performance and behavior of Tor. So consequently, the role of a defense designer is to judiciously employ these mechanisms to reduce classifier performance without incurring too large an overhead. Next slide. So there have been many different defense strategies that have been devised using these mechanisms. So for example, some of the earliest defenses opted to send traffic at a constant rate via delays and padding. This allowed for high security effectiveness to be achieved, but resulted in large overheads. As a consequence, some more efficient defenses have been developed that instead probabilistically employ random padding and are able to reduce the overhead, but don't have quite the same security degree. Then a very interesting strategy is to instead try to create traffic pattern collisions. This has the benefit of both having a very low overhead, as well as providing some provable guarantees to the security of the defense, as if you can create traffic collisions, then it's impossible to discern which real website that traffic was generated from. But a downside of this is it's oftentimes very difficult to do the precise molding required for the type of defense. Next slide. So our lab has recently been working on a new defense idea based on adversarial patches. An adversarial patch is a type of specially crafted input that can induce misclassifications in a model. These types of attacks have shown strong performance in the image recognition domain. Because website fingerprinting predominantly uses deep learning models for its classification, we may instead use these patches as a defense to confuse the attacker's model. Okay, next slide. Did it move it to the next slide? Oh, there we go. Great. So in our ongoing work, we started by defining a new style to represent traffic sequences. So here we represent traffic as a sequence of consecutive packets known as bursts. The time between packets is used with a threshold to determine when a burst begins and ends. This scheme allows for more flexible traffic manipulation than previous defenses. So we're still working on developing a robust patching training scheme. However, currently we're basing our work on the training schemes developed for the image domain patches. However, regardless, once we have a trained patch, we're able to easily mold traffic in real time to adjust a segment of the trace to match the pattern in that adversarial traffic patch. We found so far in our evaluations that this technique is very effective against attacker models that have yet to be exposed to traffic with the patch applied. However, if an attacker is able to identify what patch the defender is using and trains a new model using traffic with this patch in their representative samples, the attacker is usually able to achieve much greater accuracy, and ultimately the defense fails. Next slide. So with all that said, there are a number of general questions that still need to be addressed in defense design in the future. One particular issue is that of how much defense is truly necessary for a real-world application, since relatively small reductions in closed world accuracy can result in huge false positives and render a classifier useless. The overhead of the defense must, of course, be weighed against the effectiveness. So as a consequence, just enough defense may be oftentimes the most optimal solution for large-scale deployment, where we can't have, say, twice or bandwidth overhead, or adding 30 seconds of latency on every website visit. So finally, it's also difficult to build defenses that are effective against unknown attack techniques. For this issue, I've got no solution, as the iterative nature of research makes it difficult to predict what will happen in the future, especially for unknown network techniques and things of that nature. Okay, next slide. And that's the end of my talk. So thanks for listening. If we have time left, I could take some questions.
We may have time for one quick question. We're a little bit over.
Okay.
Is there a question? If not, please feel free to send your questions into the Jabber queue during the rest of the session, or Nate, can people send you questions directly?
Yeah, that'd be great.
Okay, cool. Brilliant. Thank you very much indeed, Nate.
Thank you.
Thanks. Okay, so next presentation is Amelia, and the topic of randomized response mechanisms in RTT measurements for Quick. So I'm going to pick up. So Amelia, if you want to. Okay, you should have audio now.
Hello, am I audible?
You are. Do you want to send your video as well?
No, it's fine. I can do video.
Great. Please go ahead.
If it's not a problem for anyone. So, thank you everyone for your attention. This is a presentation of a draft, which was published a first iteration of this text was published at some point last year. It's about the application of randomized response mechanisms in round-trip time measurements in Quick. And next slide, please. So the origins of this draft was a presentation in Pearg at IETF108 on differential privacy. In that presentation, me and Christopher Långström brought up random response mechanisms. And afterwards, it was raised by Siobhan that randomized response mechanisms might be applicable to round-trip time measurements in Quick, especially after the controversies around the latency spin bits. So next slide, please. And just as a brief recap, so differential privacy is a way to mathematically ascertain a certain level of privacy protection in the system for some definition of privacy or system. It is meant to preserve the utility of data for the user of data, which in the case of round-trip time measurements in Quick, like the spin bit, is typically the observer of the spin bit, so not the client or the server. While at the same time protecting the unique identity of the contributors of data. And these would typically, in a privacy-oriented system, be private individuals, let's say. And so differential privacy uses statistical mechanisms to achieve this goal. Through statistics, it can accomplish mathematical guarantees of simultaneous data usability and data obfuscation. But I don't want to dwell too much on the differential privacy definition in this presentation. So moving on, next slide. So just to summarize the conclusions of the investigation of using randomized responses for the latency spin bit, it does not remedy the privacy concerns that were actually raised in the Quick working group with respect to the spin bit. Because it turns out the privacy concerns that were raised with the spin bit in Quick were actually related to the utility as such. So if the utility is the problem, then differential privacy seeking to preserve utility is not a good tool of addressing the privacy problems. That said, randomized response mechanisms could also provide some form of larger degree for client autonomy over determining when a round-trip time measurement is useful and when it's not. But that would require much more precise specification of the latency spin bit, and it's also not entirely clear that it's worth the effort, that the additional privacy guarantees are sufficient to justify that kind of effort. But so next slide, please. The background of randomized response mechanisms is that it's in the 1970s. It was originally created to ensure a higher level of privacy for individuals that participate in surveys. And so originally the idea was that an individual survey taker could be guaranteed that the survey giver would not know which question was being answered, and that this would make the survey taker more comfortable in answering questions. So this could be sensitive health information, for instance, that either you ask, do you have diabetes? Or you could ask, do you not have diabetes? And since the survey giver was not meant to know which of these answers were, which of these questions were answered, that would make the survey taker perceive a higher degree of privacy, was the idea. What the survey giver does have to know is the probability that either of these questions was answered. An alternative way of thinking about this is that a survey taker might lie in the response to a single binary outcome question with some probability. Next slide, please. And so I've tried to illustrate that here. So binary outcome, of course, means that there's two possible outcomes to a question. If you have no randomized response mechanism, then the question will lead either to a yes or a no answer, or true or false, or however you want to characterize those. If you're using randomized response mechanisms, then typically having two outcomes for a single question, like survey taker can give either of two choices, gives four possible outcomes, that either they truthfully respond to the question or they falsely respond to the question. Next slide, please. And so fundamentally, the problem that you're investigating with randomized response mechanisms is how can you estimate the true number, the distribution of yes and no answers, knowing only the total numbers of yes and no responses, plus the assumed proportion of truth sayers versus false sayers. And so this has been a quite active mathematical field since the 1970s to work with different ways of solving this. It can, in general, be solved also when you have more than two possible answers to a question, but it's more complicated, and I will anyway not go into most of the maths here. But so next slide, please. So the reason that this came up in relation to the spin bit in Quick is that the latency spin bit, being a bit, actually has two states, 0 and 1. So these two states could be construed as some form of a binary outcome. And so the idea was to apply randomized response mechanisms to the state of the latency spin bit to increase privacy. And what we ended up doing mostly when I was discussing this with Siobhan is trying to practically figure out when randomized response mechanisms would, in this case, be activated to enable any form of increased privacy. And so it turns out in the end that activating randomized response mechanism in some sensible way that gave a model that could be used at least somehow required 10 additional spin bit assumptions beyond those that are already in the Quick draft in section 17.3 currently. We also needed to specify a model based on those assumptions. We included in the draft a round-trip explanation in section 7.1, just for it to be kind of a word description of how measurements and randomization would actually occur. And then we constructed truth tables for the spin bit values. There's a simulation available on GitHub written in Python by Siobhan, if anyone wants to try to simulate this. But so next slide, please. But so section 7.1 then describes 1.5 round trips in words. And one of the goals of designing the randomized response mechanism was actually finding a way of putting the spin bit in a loop, so kind of indefinitely stuck on a single value. And the reason for why you would want the spin bit to eventually end up in a loop, meaning that it no longer has any possibility of flipping from 0 to 1 or 1 from 0, is that then you can guarantee that a certain percentage of the transmitted spin bits are not useful for the purpose of latency measurements. This was a design goal since the Quick draft, in fact, assumes that a certain number of connections will not be measurable. And even if with randomized response mechanisms, you don't get exactly what is asked for in the Quick draft, you do get some form of way of, increasing the privacy levels by decreasing the utility of the data that can be derived from observing spin bits. And so there's a difference there between rendering useful a proportion of transmitted spin bits for the purpose of measurement, which is what randomized response mechanisms would do, and making sure that a proportion of the total amount of connections are not being measured as is currently specified in the Quick draft. Next slide, please. But so the interesting bit about working with like loops and randomized response mechanisms and having some probability of lying or truth saying is that you get a bunch of parameters. Like we use 3, where P is the probability that a server lies, which means that it sends a value of the bit that it's not supposed to send. Q is the probability that the client lies, which is, again, the probability that a client would send a 0 instead of a 1 or vice versa. And R, which is a random variable, discrete random variable that resets the spin bit once the spin bit ends in a loop. So these parameters can in principle be set by an observed entity like a client or a server that is seeking to adjust the privacy level of the connection, which would be in line with the user control goals of section 7.2 in RFC 6973, privacy considerations for internet protocols. In section 7.3, there are some values for PQ and R suggested that could facilitate the restriction of useful spin bit measurements, as not precisely mandated. It might be the wrong term in section 17.3.1 in the ID quick, but at least sort of going towards those goals of protecting privacy by rendering measurements useless. So next slide, please. The idea was to look for draft adoption by Pearg, perhaps not in this session, but at some time later in the emailing list. And in either case, reviews would be helpful and welcome. So just to reiterate that the conclusion is that the incorporation of such a mechanism in Quick as such is probably not worthwhile for previously stated reasons. But it's in a way interesting to look at how some of the trendier privacy protection mechanisms out there in academia could be applied to internet protocols, I believe. And so this is what we have tried to do in this draft. And well, hoping that everyone finds it interesting to study this more closely. Next slide, please. So questions or comments, if there are any.
Thank you, Amelia. Do we have any questions on this? Let's give people a minute to join the queue. Okay, it doesn't look like we have any specific questions today on this, but as you mentioned, we would very much like to see additional reviews on this on the list. And the intention is that we will do a call for adoption on this document on the Pearg list, because we do think it has some value as an example of implementing this methodology to a technique. So we do think it's useful to the research group. I don't see any questions coming through. So in that case, Amelia, I will thank you again for your presentation. Thank you very much.
Thank you.
We will move on to the second part of the presentation, which is the updates on the drafts. So the first draft we will be looking at is the censorship techniques draft. So Joe, let me grant you, oh, you're already in. You should have audio and video, so please go ahead.
Can you hear me?
Yep.
Cool, it even has a neat little sound graph. Cool, okay, so I'll be really quick. Sorry, my headset crapped out, so you may see my fancy mic in the shot. This next slide, please. So we're presenting, I guess, again, a research group adopted draft that's been in existence since IETF108, which is November 2014, a very, very long time ago. As you can imagine, it's changed quite a bit. It's fun to just troll through the diff, but anyway, we got a lot of really good feedback and pulled it from research group last call. It was clear there needed to be, sorry, I will talk slower and enunciate. It was clear there needed to be some additional work. And I really want to thank Amelia. There's a lot of authors on this draft, and they've sort of come in here and there and really helped out move it forward. And Amelia has done a wonderful job, which is why you've seen so much email from her at the list traffic. We recently submitted right before the draft deadline an 04 RG draft that deals with so much of the feedback we got during research group last call. Scaled back the definition of self-censorship. Was totally convinced that that could be smaller and still do what we wanted it to do, to point out that that's a liability here. And at Elliot Lear's urging, added a chunk about domain seizure, which does happen. So the goal going forward is try to resolve the remaining issues before a final research group last call. Next slide. this is sort of the current structure of the draft. It is basically broke down into 3 things: prescription, identification, interference, what to block, how to block, and then the actual execution of the blocking. It's in a network layer structure. You can see, if you just look at the top level sections, right? Introduction, terminology, technical prescription, technical identification, technical interference, non-technical interference. You can see there's some redundancy there that has been exposed through the editing that I think we're going to clean up. But next slide, we'll talk about the actual bigger, meatier issues. Next slide. Thank you. All right, so I've embedded the GitHub repo issue numbers and ones that are still open here. There's an open one. Elliot and Vittorio have some questions about, can we get by with a more restrictive definition of censorship? Specifically, can it be cabined to state actors rather than enterprises or merely people in position of power in a network sense? That's a pretty fundamental discussion there, and I want to talk about it on the list more, and I have a thing I'm writing up that I'll send along. I know Carsten Borman is a fan of not saying censorship techniques, but techniques employed for censorship. It's something I'm still thinking about. Chris would even, I think, an offline communication. Sorry, Chris, to expose offline communication. Hope you don't mind. That we might want to talk about network censorship techniques. It sort of would crispen it up a bit, and it's probably not a too hard edit to make. Chelsea Comlo had a really good point to make it clear with our glorious TLS 1.3 to some extent, but the increasing security of TLS. When does TLS help or hurt certain kinds of censorship techniques? That is a really good edit in adding sort of a cost to the censor in each section. It sort of dovetails with this notion that Chelsea also brought up, what they use in censorship circumvention. Censorship circumvention areas where they want to actually talk about censor maturity. Ecker, in his blinding wisdom, has a ton of actually kind of hard things to work through that's just going to take a little bit of time, and you can click on each one of those. They're each of their own are interesting, but not interesting enough to spend time talking about them right now. Still have some open issues from Stefan. There was something I wanted to postpone to the next version, which is actually integrating a really good systematization of knowledge review article. I don't know why the CS people call them SOKs. It's such a dumb name. Anyway, and I may be in a position to actually incorporate this gorgeous review article about censorship techniques actually in this sooner than I thought, given that we popped out of RG LC. Next slide. That may be it.
I think that's it. Yep,
cool.
That's your last one.
Thank you, everybody.
Excellent. Thank you, Joe. Do we have any questions for today on this draft? Joe, could you just clarify, I know you did an update recently where you addressed a number of issues. Are you planning another update with these remaining issues before suggesting we do another last call?
Oh, no. We need to do some work before we can get to another last call.
Yeah. Okay.
And by work, I mean, there's some that's just like, desk work, like, figure out what the damn thing should say. And the other is, actually, we need to talk as a research group, about some of these more fundamental things like the restrictive definition, because for many, many years, just talking about censorship has not been a problem, but for some reason, Elliot and Vittorio feel strongly about it, and I need to either be in a place where we're comfortable with it or where we can clearly say, you guys are in the rough, right? Or something like that. I don't know if that's how it works in IRTF, sorry.
So,
I don't know if there is a rough.
We'd go for rough consensus.
Okay.
That would be the initial goal at the very least. I see some questions in Jabber. I don't believe any of them are for the mic though. Please quickly correct me if I'm wrong there. Otherwise, I think you're off the hook, Joe.
Give me a good review and it'll not take another 6 years. There's not a whole lot about...
Oh, we have media jumping in, actually.
Okay.
If I can.
I was going to talk about Peter Koch's...
okay, please go ahead, Amelia.
Yeah. Well, so I think it was Carsten Borman who said on the, if I completely mangled the pronunciation of that name, I'm very sorry. that said maybe techniques employed for, that suggested changing censorship technique into techniques employed for censorship, which I thought his justification for that change was quite eloquent, and I would be strongly favorable of making this change. But I'm just wondering, since it's an open issue now, if there is anyone who has strong reservations against that change.
So people should line up and talk about it. But by all means, there's like 3 places in the document where we actually say this. So it's not a huge change. The trick is that it's in the title. And so if we're going to combine network censorship techniques and techniques, this is kind of more trivial than I think, but whatever. I don't want to trivialize Karsten's comment, but like it may end up meaning to be network techniques employed for censorship or techniques employed for network censorship, whatever. Like, I think the only sort of even minor concern I would have is that it's going to make the title long, but who cares, right? You know, okay. I'm at the point where I'm not caring about svelte titles.
And sorry. The problem I would have with something like network censorship techniques is that I have previously been in standards organizations where the meaning of the word network was discussed for extended periods of time, that I think maybe this research group is not served by having such, philosophical meanderings into what constitutes a network, actually. So techniques employed for censorship to me seemed like a good way of avoiding the ambiguity of the word network. It's just how I reasoned personally.
Okay, thanks, Amelia. And to be clear, even though you have issues in GitHub, we prefer discussion directly on the mailing list, I believe. Joe, is that correct?
Yeah, that's the plan for all of these, is to try and come to some sort of place and then actually, put text in there.
Okay, excellent. Thank you very much.
And there's a question from Peter Koch. Sorry, I'll be really quick.
Yep.
Asking about, is the censorship draft a new playing field to establish or not DNS as a content control plane? No. If that was a serious question, I'm sorry to take it not so seriously, but it absolutely not. We're trying to be descriptive and as a reference material. If you see places where we're not doing a good job of that, please send us a PR.
Okay, great. Thank you, Joe. And next presentation is on, here we go. It's by Sandeep Rao on personal information tagging for logs, which is a draft which has been shared on the mailing list. And Sandeep, let me...
Hi guys, can you hear me?
Yep. Do you want to send your video as well?
Yep.
Yep, let me just accept that. That should be coming up.
The video. Okay, great. Yeah, thank you.
There you go. Great.
Okay, great. Thanks. Thanks. Hello, folks. So let's get started. So Sarah, can take me to the next slide. Okay, so just to recap in terms of what this is all about. So in the last session, we introduced the problem of how to make log analysis a little more deterministic in terms of identifying personal information. So just to give some background in terms of the motivation of this document. So we see that as a security operators, there are many times there is a need to be able to identify personal information, specifically the exposure related to user information logs has contributed to a lot of security incidents and data leakage. So one of the very often question asked is, is there a way for us to be more deterministic in terms of identifying what is sensitive in a log, what is sensitive data in a log? So this is something that what motivated to look at this as a problem statement. So obviously, some of the things that we found out as part of this document ideation is that log itself is too subjective in terms of the format, in terms of the source and how the content. And also there are a lot of existing ways in which many products, many solutions in which there are already existing solutions where they provide us a way to identify logs. And most of these obviously are vendor specific and there was no specific guidelines in terms of how to operationalize it and possibly make it interoperable. So how can we mix and match some of these solutions in an interoperable way. Next slide. So this is what we want to summarize as the document goal. Obviously, what we want to achieve with this document is to provide that reference model. So as we know, logs have different purposes based on who is looking at the log. As a developer, obviously for troubleshooting; as an operator, maybe as for monitoring and performance measurements; and as a security analyst, more for incident response. So there is always somebody looking at the log and in a different way. So what we were looking is to see if we can provide that reference model in which how logs can be tagged and classified, so that based on where or who the consumer of the log is, there could be differential views of the log to different actors in the system. So, and that's what we want to achieve as part of the privacy control actions on the logs. So next slide, please. So this is just a quick summary on what changed from the last version. So obviously, thanks for the comments of the mic as well as on the email. So we'll try to address some of them here. So we have also tried to define a privacy schema in terms of what could be the approaches or proposals in terms of achieving something a little more unambiguous way of identifying sensitive information in the logs, and also some considerations in terms of what could be the access control model and how could those policies be defined. So that's what's the update. Next slide, please. So this is again as an illustration, as an example of what one way in which we can make these log data more identifiable. So I mean, as we all know, there are various log data that user information or user data that's included in the logs. So one approach that could be to define the namespace or a kind of identifier registry, PII registry, if I can call it. So that would at least provide some structure in terms of how these key value pairs could be represented in the log. So this would make a parsing of the logs either in the intermediary or at the consumer or the enforcement level a lot more deterministic. So because there is already a defined namespace. So this is just one example of how this can be achieved. This is something that we are trying out as an implementation as well. So next slide, please. So these are again some more thoughts in terms of how we can do the identification, again all related to privacy data. So while this whole notion can be extended to other anything that is deemed sensitive in a log, but the focus for us definitely is to look at from a log perspective. So there are different types of logs formats, some custom, some standard, syslog, CFL, CEF. So this is one extension or an extra field or metadata as we can call to the log data that would say whether a particular field is sensitive or is it critical or is it confidential. So again, these are very, at the moment, they're all proposals and just trying to experiment these models. So that's while at field level could be very useful, especially when there is a large data of log and you want to have differential actions for each field in the log. So this field level talking could be very useful for that. Another way, a lot of systems, right, we are seeing that they would rather be more interested in whether the whole log is sensitive or not. So at that, I mean, there are a lot of proposals also in terms of just identifying one extra field appending to the end of the log that says that log is sensitive or not, or confidential or not. So that is where the systems could categorize or bucketize those logs into sensitive, non-sensitive, and then have their own additional processing rules that could be worked on those sensitive logs. So that's at the log level. So next one, please. Yeah. So okay. So this is again now while the tagging at source would definitely help identify what is really important in a log or what is very critical data in a log. So also there is a need to provide the operators to define or specify what is the action that could be performed on that particular field or on the sensitivity level of the log. So again, here's one illustration that we are trying out based on at the field descriptor. So we can include some, again, a metadata where every field can be tagged with a particular log level and an action associated to say what should be a log enforcer is required to do based on the actions that's specified at the field level. So again, this is another proposal that currently being experimented to see if this can be used to execute something like a per field anonymization or per field policy actions for the log. So next one, please. Okay, so obviously there's, thanks for a lot of comments and the email comment from Joe and everyone. Like, I think they help. So we realize that it's not just about tagging something at the source. There are a lot of other challenges in terms of the transformations of the log as the log gets propagated through different hops in the system, the log pipeline. There is always change in the way the log could be formatted, or it could be changed in the format of the log. So one of the problem is how do we look at privacy preservation so that can be kept as the log gets transformed, extracted, loaded into different systems. So another area that's still not investigated is in terms of change of authorization. I mean, change of policy. So basically, if there is a change in the marking or the privacy specification of certain fields or certain data elements, so how do we enforce that change in the system? And the final one is around out-of-band mechanisms to notify privacy systems. This is largely about systems, legacy systems where a lot of log generation is already happening, and that's a bulk of it as we see today. So how do we insert something like a log mechanism to a notification mechanism so that we can inform what is private and what is not private, or what is sensitive or not sensitive. So that's an out-of-band mechanism work that we can look at. So final one, please, slide. Okay, so again, this is open questions in terms of if you have any questions, and in terms of whether we should continue this work in Pearg, and if there's a need to change the scope, and are we ready for now adoption. So any questions?
Thank you, Sandeep. That's great. Do we have any questions on this? Okay, we have Stephen Farrell. Let me enable the audio. Off you go, Stephen.
Yeah, I kind of support doing this work. One of the things about logs I've noticed is that anything that has a field that takes a human input always ends up containing a password or something out of the paste buffer. So I'd suggest you consider tagging based not just on the kind of data type, but also on the source. But generally support it.
Yeah, thank you. That's a good input.
Do we have any other questions in the queue? I think I see one in the chat.
There's one question. Obviously, why is the example from a really RFC? Yeah, absolutely. Yeah, thanks for that input. Yep. So we can trying out some of the systems, and obviously, that's one of the log source that we had, and we tried to do that. Yeah, I'll ensure that we move to a later and better version of the examples.
Okay. That's great. Thank you very much then indeed, Sandeep, for that update.
Thanks, everyone.
And we will be raising the question of adoption on the list for this draft. There will be a call for that, just to confirm. Thank you.
Thank you, everyone.
Okay, and now to our last presentation. Gurshad Grover is going to whisk us through an update in the last few minutes on the draft for performing safe measurements on the internet. Please go ahead, Gurshad.
Hi. So yes, very quickly, this is guidelines for performing safe measurement on the internet, which is a draft mostly written by Ian Learmonth, and I'll be joining as a co-author in the next update. So this presentation is just to run you through the open issues and to welcome any inputs. Next slide, please. So yes, this is a draft aimed at researchers who are running network measurements, and the guidelines are, to quote Ian's working definition of safety, which is when performing research on a platform shared with live traffic from other users, the research is considered safe, and if and only if users are protected from or unlikely to experience danger, risk, or injury in the future due to research. Next slide, please. And currently, we have a few sections on consent and other safety considerations, mostly relating to traffic. In the interest of time, I'll sort of focus on the issues. Next slide, please. Yes, so I'll start with the last one, which is safety, not ethics. And this is a scoping issue, perhaps, and some of the, I think, comments that came in earlier sort of tried to address the scope. And so this draft is not, as it clearly notes, not meant to supplant any institutional ethics process. It's just documenting a subset of that, which is safety. The aim for the next version is to add recent research, from instance from the workshop on ethics in network research systems. Then there's currently no statement on future threats that might arise to safety. So that's something like encrypted payloads that are being processed, but could be sort of broken or decrypted in the future, or could be fed into some machine learning models that are currently not operated today. So things like those. So yes, these are on GitHub as well, but any additional comments on the mailing list or directly are very welcome. I'll stop for now.
Thank you very much. We did have one person in the queue who's just popped out again, though. We have a couple of minutes, so we'll just wait and see if any other questions come through from the queue. No, it doesn't look like it.
Okay, and I think Ian is also on the chat and group. So if Ian, if you feel like adding anything important that I missed, please go ahead.
And this draft is adopted already. It's just that we're having an additional author coming on board for the next update. So we expect to see a reasonable amount of changes. Okay, I don't see any questions for you today. So thank you very much indeed, Gurshadbad.
Thank you.
And thank you, everybody, for joining today's session. Thank you to all our presenters today. And thank you for the gods of Meet Echo for smiling on us. We managed to make it through the session. So we look forward to seeing everybody again, hopefully at our 109 meeting. Thank you very much, everyone. Goodbye.
Thanks, everyone, and all the presenters. Bye.